So this is the third part of chapter 5, linear programming. uh, Everything is exactly same here, just an addition of objective function which we try to minimize or maximize with respect to our linear inequalities or linear constraints. So here the student will able to solve application using linear programming method. So we have already discussed this bounded region. Any region which is enclosed is called bounded region. If it is not enclosed, let's say like this, it is unbounded. So a familiar example is like we saw this example in the previous section 5.2. Suppose a manufacturer makes two types of skis. Everything is exactly same, but now here is the twist. This is the additional part which I said that we will have an objective function. Suppose the profit on each trick ski is 5 and profit on each Sorum ski is 10. How many of each trick ski should be manufacturer produce to earn the greatest profit? So the profit function is 5x plus 10y. So how many solemn skis and how many trick skis should we produce with respect to those constraints? We have to satisfy those constraints to get the maximum profit. What does it mean by satisfying those constraints? Like when you start a new business, you have some constraints. The very first constraint is your budget. Maybe you have $100. Now within this $100, how can you maximize your profit? Now you have to split this $100. You have to pay the bills, you have to pay the rent, you have to pay the labor fee, you have to buy the raw material, whatever you want to manufacture within, and you will decide that how much will you spend on the raw material, how much should you spend on the labor salaries or things like that. So all these are the constraints. So we have to satisfy all those constraints, and within those constraints we have to maximize our profit. So similarly here, this is an example. These are the constraints that we cannot produce more than 15 solemn ski. Here there was a constraint, if I can remember, here this one. And we have 180 hours, we cannot work more than 180 hours. And there is another constant, we cannot work for more than 160 hours for finishing or assembly, something like that. So these are the constants. Within these constants we have to maximize our profit. So this is an example of linear programming problem. Every linear programming problem has two components. A linear objective function is to be maximized or minimized. If you have cost function, we have to minimize our cost, and if we have profit function, we have to maximize our profit function. A collection of linear inequalities that must be satisfied simultaneously, these are called the constraints. Like so far in exercise 5.1 and 5.2, we were only dealing with the constraints which we were calling them linear inequalities. Now onwards we will call them constraints, limitations, and within those limitations or within those constraints we have to maximize our profit or we have to minimize our cost function. So this was an example which we were solving in the previous section as well, and everything is same. We will make the feasible region for these constraints, and this is an extra additional part which I was saying, the objective function. So when you will plot all those constants on the same graph paper, it will be like this. And now, as I said, we have already discussed this part earlier, that we will round it down. We will make 7.5 to 7. We will not make 7.5 to 8. We round it down. So that, why we round it down? So that we should be within feasible region, we should not go outside the feasible region. If we make it 8 and 13, we will move outside the feasible region. So now we will substitute all the corner points one by one, and we will see where we can get maximum profit. So we will substitute all the corner points one by one into this function, and we will see where we get the maximum profit. So when you will substitute 7 and 12, you will get maximum profit. So this is our solution. 7, we should produce 7 solemn keys and 12 tricks key in order to get the maximum profit. So corner points, at least one corner point will be our solution. If a linear programming problem has a solution, it is located at corner point of the set of feasible solution. If a linear programming problem has more than one solution, at least one of them is located at corner points. So these are just definitions, you can just go through from it. And corner points, and yeah, maximize the quantity. We have to maximize this constraint, this objective function within these constraints. So first of all, we will plot, we will try to figure out their corner points by plotting them, and determine the corner points. So you see, we don't have, this is unbounded, we don't have any bounded solution. So we conclude that this linear programming problem has no solution because it is not bounded, it is unbounded. When it is unbounded, we will say that it does not have any solution. So here there is another example. The additional part is, we have an objective function. The company makes a profit of 25 on each 2% board and 40 on each 4% board. So if 2% board is represented by x, then 25x plus 40y. We have to maximize this objective function within those constraints. When we formulate the problem, I think we didn't solve it here in the PPT. I solved this problem in the solved example part, where you can see that how we can maximize the profit. So these are the constants. This is the first constant, this is the second constant, and as I said, these are the built-in constants. We always consider them. When you find the feasible region, you will get these corner points for this particular example: 0 0 0 480 480 240. Now we substitute all these points one by one into our objective function, and we will see where we can get the maximum profit. When we substitute 0 0 corner points into the profit function, we get 0 profit. When we substitute this corner point into the profit function, we get this much profit. When we substitute this point into the profit function, we get this profit, and when we substitute this point into the profit function, we get this profit. So this is the maximum profit when we substitute 480 and 240. So 2% boards, we should produce 480 2% board and 240 4% boards in order to get the maximum profit. So similarly, we have this objective function. Within these constants, we see where we can get maximum value for the situation is same. You will plot this equation, you will plot this equation, you will plot this equation, you will figure out their corner points, you will substitute all the corner points one by one into this equation, and you will see where you can get the maximum profit. So here it comes. When you plot this equation, this equation, this equation, you will get their bounded region. Here this is your corner point, this is your corner point, this is your corner point. What are those 3 points? Here we have listed down these 3 points. So you substitute all these 3 points one by one into the objective function. We see z is 40 in first point, z is 40 on second points. So these 2 points are optimal solution. You can choose either this one or that one, both are fine. So the multiple optimal solution, as I said, we have seen in the previous example, you can have multiple optimal solution, that does not matter. So the solution to example 3, the multiple solution in general, if 2 corner points are both optimal solution to a linear programming problem, then Any point on the line segment joining them is also an optimal solution. Thus, any point on this line and where x between this such that 3 would be an optimal solution.